This video is going to begin chapter 2 on logarithmic or exponential and logarithmic functions. So section 2.1, we're going to cover exponential and log functions of natural base e. We covered general properties about exponentials and logs back in chapter R. This section focuses specifically on those that have base with the number e. So we're going to talk about how to graph and solve exponential functions of that base and graph and solve log functions of that base, mostly solving. All right, so the definition of this number e that they refer to as the natural base is found by taking the definition of that number e is the limit as n approaches infinity of 1 plus 1 over n to the nth. So if you were to make a table of values of this function and let the value of n get increasingly large, this is the decimal that value would approach. This number occurs a lot in application problems and in other things we're going to see later on. It's widely used in the field of calculus. Okay, so we just give it a special name. It's kind of like pi, right? Pi has a special name. We call it pi because it's used a lot in formulas, but it's this long irrational decimal. Okay, so e is similar. So the value of e is approximately 2.71828, etc. It never stops and never repeats. So it's about 2.7. All right, so our first application here is we're gonna use e within a formula, and we're gonna do the application problems first. So this is about continuous exponential growth. So basically compounding future value of an investment given interest rates, time, and other information. So a quantity p growing continuously, so if it says that you're compounding interest continuously at annual percentage rate given r, we will always express r in decimal form in our formula, has a future value after t years given by this formula. So the amount you'll have after t years if you deposit p dollars in an account is found by taking how much you deposit p multiplied by that number e raised to the power of the interest rate as a decimal times the number of years, r times t. If your quantity p is not growing continuously but being compounded a finite number of times per year, we'll refer to that number as n, then the future value becomes this formula. A equals the amount you invest p times the quantity 1 plus r is the interest rate divided by the number of times it compounds per year to the power of n, which is again that same number of times per year you're compounding, times t, which is the number of years. So our next example utilizes both a finite number of compoundings in which this formula applies, and if it says you're compounding continuously, we'll use the formula that has the e in it. All right, so this is our formula at the bottom here. We'll get to that part in a minute. So let's say Lewis invests $5,000 in an account that earns interest at an annual rate of 3.25%. We want to find the future value of Lewis's account after 5 years if interest is compounded first annually, meaning 1 time a year, b monthly, meaning 12 times a year, because there's 12 months in a year, c meaning daily, meaning 365 times a year, once a day, and then finally d continuously. All right, so for parts A, B, and C, we have annually, monthly, and daily interest compounded a finite number of times per year, so we have to use the formula A equals P1 plus R over N to the NT. All right, so for part A, we have P equals 5,000. That's how much he's going to invest. The interest rate was 3.25%, so converting that to a decimal, 0.0325 for 5 years, so T is 5. Compounding annually means N is 1 time a year. So after 5 years, his account will be worth, we're plugging into that formula, P was 5,000, 1 plus R in decimal form divided by N, 1 to the power of N times T. So 1 times 5. Use your calculator to put all this in. You should get the value $5,867.06. You'll round to the nearest cent. All right, part B, compound monthly, means the only thing we're going to change here is the value of n. So monthly means you're going to compound 12 times a year, so that means n is 12. So we still have the 5,000 principal, 1 plus, interest rate is still the same. This time we divide by n, which now is 12. And then the exponent in the formula is n times t. So again, this n has to change to be 12. So putting that into your calculator, you should get $5,880.95. Notice it's higher than it was here because you're compounding interest. You're adding on the interest value more times during the year. All right, this would be part C. Compounding daily means n is 365. So after 5 years, his account will be worth 5,000, 1 plus 0.0325. This time n is 365. So that goes here and here. Everything else stays the same. Plug that in your calculator, you get 5,882.20. And then finally, part D means interest is being compounded continuously in part D. So that means our formula is going to involve A equals P e to the RT. So when you see the word continuous, you change to this formula. So 5,000 is still our P. E, there's a button on your calculator for that number. Interest rate goes up here this time. 0.0325 is the interest rate. And then T is still 5. So on your calculator, you should have an E button. So if you're on a graphing calculator, you just type in 5,000. And then you find your e to the x button, right? So to find that, and then you're going to put 0.0325 times 5 in the exponent. So if your calculator is such that you get a little box, you can just type that in. This times this is fine. Or if it doesn't give you the box, it just gives you the exponent, the caret, then you're going to have to put parenthesis 0.0325 times 5, close parenthesis, to make sure it multiplies all that together as an exponent. Right, so I would practice on utilizing your calculator to make sure you're getting the right answer, but this is what should be what you end up with when you're finished. 5,882.24. So you got to pay attention to if you're compounding a certain number of times a year or if you're compounding continuously. That'll determine the formula you should be using. All right, moving on here to logarithms. So any positive number x, the natural log, or in other words, the log that has base e, that number we talked about at the beginning of the section, is given by this notation. Natural log means ln. We abbreviate it with the symbol ln of x, and that simply means log with base e. We talked about logarithms again also back in chapter R, the beginning of the semester. So log base e, just like a log base 10, you just see log with no 10 at the bottom, right? So if they're meaning log with base e, you're going to see this symbol natural log of x. So there should also be a key on your calculator with an ln on it. So when you utilize that key, it's calculating the logarithm of base e. So using our log properties, y equals natural log of x is equivalent to, if the base is e, this would mean e to the power of y is equal to x. That's the equivalent exponential form. All right, so example 2, find each of the following. If necessary, use a calculator to approximate. So you're using your calculator here. Possibly. You don't necessarily need it, but you could use it. Natural log of e to the 4th. All right, so you could use your calculator and type your natural log key, then pull up e, put in a power 4, and have your calculator do that. Or if you remember the log properties we talked about in chapter R, or you may have learned in a previous algebra course, we just said that this function is defined to be a base e logarithm. So since the base is e and this base is e, the answer should just be 4. That's one of our properties. So y equals natural log of e to the 4th is equivalent to, you could write this as e is the base to the power y equals the inside. So if e to the y equals the inside e to the 4th, right, that means the y has to be 4. Or just knowing that the base e matches the base here, which means that the answer is the exponent. All right, second part, natural log of 1. Any log of any base of the number 1 should be 0. Okay, or you can think of it using the definition. So if y equals natural log of 1, this means e to the y equals 1. So e to what power is equal to 1? E to the 0 power is equal to 1, so the y would have to be a 0. Or again, the calculator will tell you that. Okay, here's just like part A. The base is e, this base is e, this answer should be -1, right? or knowing that this means y equals natural log of e to the negative 1 means the base e to the power y equals the inside. So e to the y equals the inside e to the negative 1. So since they're both base e, the powers must match. Or again, the calculator. There's lots of ways to do these. Natural log of 20. Here they're just going to tell you to use the calculator, which you could use that all along on the others as well. So natural log, put in a 20, 2.996. This one you can't do any other way because the base is e and you can't write 20 using the number e. Like these numbers, right, utilize that same base, so we can simplify without the calculator. All right, properties of natural logs. Same properties we talked about in chapter R of regular logs. The natural log of a product is the sum of the logs. Natural log of a quotient is the difference of the logs. Natural log of m to the power k means you can drop the power down to the front and write that as k times natural log of m. Natural log of e is always 1 because the bases match. Again, base matches the base means the answer is the exponent. The first three require m and n are both positive. Natural log of 1 is 0, right? The log of any base logarithm of 1 is 0. And then change of base formula also works for natural log. If you have to evaluate a log base b and you don't have the template to type in the b, before we did it like this. We did the common log of m divided by the common log of b, or you could use your natural log key. You can change it to any base you want. So as long as you use the same logarithm top and bottom, it doesn't matter. Natural log of e to the x would be x. Again, because the base is e, matches the base, you get the exponent as your answer. And then here's, if the power is natural log x and the base is e, because the bases match again, we just get the value of x. Okay, all of these, I know I went through those really quickly, but we've covered them already, and you should have seen them before you got to calculus. All right, so those were all covered in chapter R. It's just now we're applying them to the natural log definition. All right, natural log of x exists only for positive numbers x. So in other words, its domain, the thing you're taking the log of, must be positive. So if it's just an x here, it's got to be greater than 0. And it's always increasing, and if you looked at the graph, the range would be all real numbers. All right, find the domain of f of x equals the natural log of 5 minus 2x. All right, so 5 minus 2x is sitting where the x typically would be. So 5 minus 2x, that expression, because that's what you're going to take the log of, it's all in parentheses, that thing must be greater than 0. You can only plug in a positive number to a log function. So we're going to solve that inequality. So we subtract the 5 from both sides and get negative 2x greater than negative 5. We divide both sides by negative 2. So notice when we divided by the negative, the sign switched direction. So negative 5 divided by negative 2 simplified to positive 5/2, but this flipped around, right, because we divided by the negative. So x less than 5/2. So that means our domain in interval notation would be negative infinity up to 5/2, not including. This is always strictly greater than, so we're not going to include 5/2. So you have a parenthesis on the end. All right, let's try another domain problem. Find the domain of natural log of 7 minus 3x. Same thing. Solution, 7 minus 3x must be greater than 0. You can only take the log of a positive number. Subtract 7 from both sides. Divide by negative 3 means you flip the sign again. So you get x is less than 7/3. So that means in this case the domain is negative infinity up to 7/3. All right, here we're going to solve some exponential equations. Solve the following exponential equations using logarithms. Give answers to 3 decimal places. All right, part A, e to the 3x equals 2. Part B, 250 e to the 0.015t equals 750. So these both have a variable within the exponent. All right, so e to the 3x equals 2. Step 1, take the natural log of both sides. If I need to solve for the exponent of e, I need to apply natural log in order to do that. So once you have that exponential part by itself, which it was given that way, e to the 3x was all by itself, we can take the natural log on both sides. So when I take the natural log here, the benefit is that because that's base e and this is e, this will simplify to just 3x. The other side will stay natural log of 2. And then we can just divide by 3 and get the value of x. So the natural log of 2 divided by 3. And then on your calculator, you would just simply type ln2, close your parentheses, divide by 3, and hit enter, and this should be your decimal. All right, second part. 250 e to the power 0.015t equals 750. We're going to do the same thing here, but we first need to get the e to the power all by itself. Okay, so we have to isolate the exponential expression. So all we did here was dividing both sides by 250. So we get e to this power. If I divided this by 250, it cancels. 750 divided by 250 is the 3. All right, now we can take the natural log of both sides like we did before. So apply natural log to both sides of my equation. On the left, the base of the natural log is e. The base of that exponent is e, so that left side simplifies to just the exponent, 0.015t, equals, the other side is still natural log of 3. Then we divide by the 0.015. So we get t equals natural log of 3 divided by 0.015. And when we use our calculator and type that in, we should get 73.24. All right, there is a part of one of the problems on the homework that asks you about doubling time. All right, so the exponential growth rate r, which is like the interest rate in the interest problem we did earlier, expressed as a decimal, and the doubling time, in other words, time it takes for an amount to double, we'll call that capital T, are related by this equation. Growth rate as a decimal, or interest rate as a decimal, times the doubling time is always equal to natural log of 2. So I can rearrange this however is convenient for the problem. So I could write this as r equals natural log of 2 over t if I wanted to solve it for r, or I could write this as t equals the natural log of 2 over r if I wanted to solve it for t. So all three of those are equivalent. All right, so let's try an example. Facebook connects people using other members they designate as friends. During its period of heaviest growth, membership in Facebook was doubling every 6 months. What was the exponential growth rate of Facebook membership as a percentage? So here we're going to calculate R using that formula. All right, so if I solve that formula for R equals the natural log of 2 divided by capital T, where T was the doubling time. Here, if it says it's doubling every 6 months, our doubling time, or our T value, is 6. So that means the growth rate is the natural log of 2 divided by 6, or 0.116. So as a percentage, if it says to state it as a percentage, 0.116 means that its membership was growing at a rate of 11.6% per month. So to convert this back to a percent, we move the decimal to the right 2 places, or multiply by 100. All right, next example, we're going to solve a log equation. So this time we're solving for x within a log. So before, when we solved for x within an exponent, we had to utilize logs. Here, since we're solving within a log equation, we're going to utilize e. All right, so our first step here is going to be to get the log expression by itself. All right, so start by isolating the log. So if we start with this equation, we want to get natural log of x plus 3 all by itself. So step 1 would be to subtract 5 from both sides, giving me 7 natural log of x plus 3 would equal 14 if I subtracted 5 on both sides. Then we're going to divide by that 7 that's out in the front, so that would give me natural log of x plus 3 equals 2 if I divided both sides by 7. All right, now we're going to, so this is a log equation, we've got the log by itself. So remember the definition, remember ln means the base is e. So this is equivalent to saying e to the second power equals the inside. That's what we're going to write. They wrote it the other way, but it means the same. The inside, x plus 3, is equal to the e to the second. And then we can subtract 3 from both sides, so e squared minus 3 would equal x. And then on our calculator, type in, use the e button to the power, you can put in a 2, and then subtract 3 from that, and you get 4.389. All right, so the summary of how the problems in this section work are what we used. Natural base E, that number defined as a limit, is approximately 2.718. Continuous exponential growth, we had a formula that involved that E. We also had a formula that involved N if we happen to be compounding using that was not continuous. Exponential growth rate and the doubling time are related by the growth rate times the doubling time equals natural log of 2. And I can use any version of that formula here. The natural log of x is given by this notation, ln of x, meaning that it's log base e. Y equals natural log of x in exponential form. This is equivalent to saying e to the power of y equals x. The function natural log of x is always increasing. It has a domain that is only positive numbers to plug in here, and the range is always all reals. All right, so that is the end of section 2.1.